can use these techniques even in pretty particle-laden environment. I think, yeah. Well, this is also interesting because we were asked by a boiler company, would it be possible to measure in a huge furnace when you introduce ammonia? You know, ammonia can be introduced to reduce the NOx. And in this furnace, which I think was on the order of 5 meters, would it be possible to visualize the input of ammonia or the liquid into the furnace? And then we have the problem, as I described yesterday, that here we have inspection holes like this. How could we possibly do measurements? Fortunately, in this case, we have 2 inspection holes so that we can emit the laser in one, and then we put in a borescope, water-cooled borescope that looked on the expanded laser sheet. So we have a laser sheet that is expanded and having a sheet like this, 1.5 meter, that goes through, and then we could, at 90 degrees with this borescope, look in 90 degrees, and we could visualize the ejection of the liquid. This is where a lot of images were accumulated, and these are single shots. Once again, these are for demonstration purposes. That these techniques can be used also in big, large-scale furnaces, together with modeling to see where is this liquid introduced, when does it disappear, and how could you optimize this. Okay, I think this was the end of the fluorescence. Now we are switching to completely different techniques. Now we'll describe a little bit on Rayleigh and Raman scattering. Are you familiar with Rayleigh-Raman scattering? Have you heard about this? Yes? Okay. So it's sort of techniques that are related. So I will start with Rayleigh scattering. Just a question. Do you know why the sky is blue? Some days, at least yesterday, the sky was blue. Why is it blue? Well, it's blue because you have the sunlight is hitting molecules, and you get Rayleigh scattering when you hit air molecules. And the Rayleigh scattering is proportional to 1 over lambda 4, 1 over the wavelength to the 4th power, and that means that the scattering of the blue is much stronger than other wavelengths. That means that if you look at the sky, the sun is shining on the molecules, and you see preferably the blue light. In the same way, when the sun goes down, or in the morning, and you look into the sun, it looks red. For the simple reason that most of the light is scattered, and the remaining is red. Right? I mean, if the blue light is scattered when you have a long distance at night or in the evening, then the red is remaining. That's why when you look in the sun, it looks red. So this is purely dependent on the Rayleigh scattering. So that's scattering from molecules or very small particles as compared to me scattering, which is scattering at the same wavelength from larger particles. And that means that you have the 1 over lambda 4 dependence, that you preferably should use a short wavelength laser as compared to one in the red. So Rayleigh scattering has been around for quite some time together with Raman scattering, for the simple reason that here you don't need to have any tunable laser. So you can use any laser. Just illuminate the molecules and you look at the scattering. The only thing you have to consider is that the bluer, the better. And you can do mainly it has been used for temperature measurements. And you can do 2D measurements as will be shown. In principle, you can also make concentration measurements. The problem is that for the Rayleigh scattering, all scattering takes place at the same wavelength. So if I illuminate a sample with a lot of species, all of them will give rise to the same scattering. So it's not easy to distinguish one species from another. But in principle, I mean, if you take advantage of that some species have a very high cross-section, high probability to scatter, like hydrocarbons, then of course if you have an injection of a fuel which is pure hydrocarbon and you make an experiment, then you can say that almost all of this scattering comes from the fuel, since the scattering cross-section might be 2 orders of magnitude higher. So there you can sort of get some at least fuel separation from the air. So this is an advantage. But it's not possible to distinguish between nitrogen, oxygen, carbon dioxide, CO. All of them are at the same wavelength. So the scattering, it's pretty simple. You have a laser, as I said, at any wavelength. It illuminates your object, then you image that with a lens onto a detector. Very simple. And your signal is proportional to the laser intensity. It's proportional to the number of species. Remember this, the number of the scattering object. It's proportional to the length, which you are averaging of. It's proportional to the how many photons you detect, how big lens you have. That's the solid angle. The efficiency of the detector, and also very importantly on the cross section. And that is sort of could be a problem with Rayleigh scattering, that each species have a distinct cross section, probability to get scattered. And that, I will come back to this. But this is a sort of a problem, because what you see here is the effective cross section, meaning that you have for each species the species concentration times the individual cross section. Then you sum this up and then you get the total cross section. And if you have a mixture, then you might think, how could this possibly be used for temperature measurement, because you don't know necessarily the concentration of the different species. But I will come to how this can be handled. So here you have the formula, and now if you use the perfect gas law, you know that the number density, the signal is proportional to the number density, but the number density is inversely proportional to the temperature, right? So if I have a signal and I heat it up, then the signal goes down, exactly according to this. So it's a very simple way to get the temperature. If the signal goes down by a factor of 2, the temperature has gone up by a factor of 2, according to this. So just to see, and you can extend this to get a two-dimensional, and here is an example. If you assume that you have a measurement in one case, the temperature is 300 K in this point, and in point B, the signal is factor of 5 stronger in A than in B. Then we can very easily calculate the temperature by this. If the signal is factor of 5 stronger here, it's a factor of the temperature is factor of 5 higher there. So there directly we can measure the temperature to 1500 K. Very simple. But then we have the warning that we have the differences in Rayleigh cross-section. And here is just, you can see the cross-section, oxygen, nitrogen, hydrogen, CO, CO2. And there when you come up to this hydrocarbon, you have a very high cross-section. So then the question is, how can we measure temperature in a flame where we don't know the composition? Well, if we just look at this, how the cross-section changes from unburnt gas and a burnt gas using methane air as a function of equivalent ratio. Then you can see, just by accident, that up to equivalent ratio of roughly 1, the cross-section is very similar. It just happened to be that if you compare the unburnt gas, which is then oxygen, nitrogen, fuel, with the burnt gas, which is preferably carbon dioxide and water, it just happened that they are the same up to a certain stoichiometry. So here you can do a lot of experiments. If you go to a richer flame, then you have to watch up. So that's why Rayleigh scattering preferably should be used, must be used below roughly equivalent ratio of 1. And then just very simply, I mean, here is the background along a line. If we have a flame and we send in a laser above this flame, without the flame, but above the burner, you can see that this is essentially giving the intensity which is caused by the sensitivity of the detector. Then you put in the flame, the signal goes down, and then you just compare how much it goes down as before, and then you can convert this, I would say, very easily to the temperature. And this is at different height above the burner, 10, 20, 40, 50 millimeter. This has been used quite a bit, and here is a two-dimensional image. Very similar setup as before, YEG laser, cylindrical lenses, send the sheet into the burner, and here you can see how the signal goes down and convert this to a two-dimensional temperature map. So it's very simple. However, you might see, well, I can come back to that a little bit later. Just remember this picture. I will return to this. And then you have the advantages of Rayleigh scattering. It's a very easy technique. You can use almost any laser wavelength as long as you look for the 1 over lambda 4 dependence. The signal is proportional to the number densities and then inversely proportional to the temperature. And you don't have to worry about saturation or quenching effect. So it's a very attractive technique from that perspective. Then you have certain limitation. All scattering, everything takes place at the same wavelength. And you have to know this cross-section is in principle when you have to convert the signal to the number density, to the temperature. It's an incoherent technique. And then a very important part. If I go back now, you can see here these dots. What's that? most probably it's dust particles. And remember that the particle, me scattering particles, is much, much stronger than the Rayleigh scattering. So that will destroy our signal severely if we have a sort of particle soot in the flame. That's a strong limitation. And also, that in principle, that could be avoided with very advanced, what is called, with the Rayleigh scattering, if you use a very specific laser line width tuned to an absorption line of an atom, and then you can sort of take advantage of that. The laser scattering is very narrow, and the Rayleigh scattering is broadened. So you can, with pretty much of going to more advanced lasers, you can filter this, but it's pretty advanced. So this is called filtered Rayleigh scattering. That has been some demonstrations about that, but I would say that it's a little bit too complicated. Another disadvantage is, of course, if you want to do experiments in engines, gas turbines, you have to go through windows. Where did I put my... If I have, this is my engine, here I have window, right? If I go in with a laser like this, it comes out, but you have reflections, so that when this beam hits a surface, roughly 4% of each surface is reflected, so you get from both this surface and this surface reflects going back. So you have a reflections at lower intensity, but that means that you will essentially create a light bulb. You'll create this will, if you look into this from the side, you will not only see the laser beam, but it will be, if you use a green beam, it will be like a light bulb at the same wavelength as we are detecting the Rayleigh scattering. And that might be a problem. There are also ways now how this can be get rid of by using striped illumination, similar to Sleepy. That was we presented at the last symposium. But this is still sort of just a demonstration. But in principle, we have problems because we are detecting at the same wavelength as the laser, both for particles and for reflections from windows. Okay. Then we know what Rayleigh scattering is. Then it was discovered already in 1923 by the Indian scientist Raman, and he got the Nobel Prize for this 32, 33 or something, in the 30s at least. And what he discovered was that when you illuminate a gas sample, of course you get Rayleigh scattering, but you also get scattering at other wavelengths. And that was the Raman signal. And these signals are different at different wavelengths, depend on what species you have. And I won't go into any detail, but essentially when you illuminate a sample, or a molecule, you induce what is called a dipole moment. And this is proportional to the polarizability times the electric field. And you can write the electric field like this. This is the polarizability, I'm sorry. This is the polarizability, this is the electric field. The electric field, you have the frequency of the laser. You know that exactly. Here you see that you have a constant, and then you have a term that includes another frequency, and that is exactly the vibration frequency. You remember the molecules have vibrations. And now, if you just multiply the polarizability times the electric field, you get something that is shown here, right? It's essentially just multiplying two sinus function, and you will end up with something like this. That means that you have one term at the same wavelength as the laser. This is the Rayleigh scattering. This is sort of a description that you have a frequency at the same wavelength. But then you get two other components. One where you have the frequency of the laser minus the vibration of the molecule. And the other with the vibration of the molecule plus the frequency of the laser plus the vibration. And the vibration could be converted into an energy. And that means that you have one component exactly at the laser wavelength, right? And then you have components shifted to the high frequency side and the low frequency side, where the shift is the vibrational shift. And each molecule has a different vibration. So that means if I have a green laser, then all the Rayleigh scattering comes there. Then if I look for other frequencies, I could see that I might have one yellow, one red, and if you measure the frequency, the wavelength difference, and convert that into frequency, you can see that this is exactly where oxygen will occur. This is exactly where nitrogen will occur. So just by looking at the different wavelengths, you can deduce what species do you have in the sample. So this is also a pretty simple formula. You have the number density, laser intensity, cross-section, detection, angle, and the constant. Essentially, I mean, you have everything that you can measure. The important is that you have this Raman shift, the vibration. And you can look in the literature, you have a lot of different molecules. And then you can see that as I said, oxygen has a Raman shift, a vibration frequency of 1556 wave numbers. And that means if you have a laser at 532 nanometers, convert that to wave numbers, add or subtract 1556, you will end up at 580 nanometers. You know exactly where you would look if you have that wavelength on the laser and oxygen or nitrogen or CO or CO2. So just by having all this tabulated, you can directly, by looking at the color that is scattered from the species, and moreover, you can look at the intensity. Here you can directly convert the signal to absolute number densities, as compared to laser new fluorescence, where you have a lot of problems. So this is a very, very nice technique in order to get what kind of species you have and how much of the species you have. So just, if you like, a task, if I have a laser at 532 nanometer, I have 5 minutes, okay? If I have 532 nanometers, where should the vibrational oxygen Raman peak appear, and how strong would it be from air if the nitrogen peak is 1000 count? So how do I do this? Well, it's not that difficult. If we go to the table, we see that the Raman shift is 1556 wave numbers. If we excite at 532 nanometers, that means that we have 18,797 minus 1556, getting to 17,241 wave numbers, meaning 580 nanometer. So if we use this laser, we know that all oxygen should take place at this peak. And that could be converted to other species as well. And then we can calculate the signal strength of oxygen in air, and we take into account how it is in the air, and we can come out with how many counts we'll get from this peak. I will just go into the experiments. Here are some old experiments we made some years ago, where we put into a cell. We wanted to measure in a cell from various species, and we tried to investigate the detection limit, and we came up with on the order of 800 ppm. We looked at spectra from a Bunsen burner. Here was just above the burner, we see a lot of hydrocarbons, oxygen, nitrogen, water, and then above the flame we got the CO2, CO, the oxygen decreased, and we got even hydrogen. And here we know exactly where to look. This is where we analyzed flames from a small fire. And here we looked at the signal from different species, oxygen, carbon dioxide, and CO, as a function of time. So here we started with 21% of oxygen, 0 of CO and CO2, and you could see how the concentration changed as it started to burn, and then after 5, 6, 7 minutes it goes back to the normal. I have to skip a little bit. It has been used for engine measurements to compare directly the air-fuel ratio in an engine. I didn't say maybe explicitly, but you have a main problem with Raman, and that is that it's a very, very weak signal. It's a very weak signal. And that means that you have to work very hard to get 2D measurements, which is hardly possible. And the sensitivity is not that high. So that's why this technique has not maybe launched in the community for practical application. And you have a problem because if you want to use high power laser, you get breakdown, as I said before. You just break down the air. You won't be able to use it. You can stretch the pulse, but it's still a problem. So what we are working with now is a laser normally used for high-speed measurement, but now we have a lot of pulses, but the pulse energy is low. That means that we have an power on the order of 100 watt in this. And not only that, we could also make the multi-pass out, so the beam goes back and forth up to 70 times, which we have shown. So that means that we can go up to kilowatt without disturbing, and that will hopefully, we are not there yet, we hope that this technique with this could be even so that we can go down to maybe 100 of ppm that could be applied, and especially if we go to high pressure, where we gain because you have a higher density. These are experiments, preliminary experiments in a high pressure burner, where you can measure oxygen, nitrogen, methane, water, and hydrogen, and compare to models. Now I think that this technique might help to make Raman more applicable with this. So you have a lot of advantages, I have said, with the Raman scattering. You don't have any quenching. You have possibility to directly measure quantitative. You can go to high pressure. You don't need any tunable laser. You can measure essentially all species at the same time. All major species can be measured at the same time. But you have the limitation, previously at least around 1000 ppm, which we hope to increase in the future. So essentially the main disadvantage with Raman scattering is that the signal is very low. But there has a lot of potential if we have a new laser source. Am I running out of time? Okay, I thought maybe I could show something about cars and laser-induced incandescence and other techniques, but we have to do that next time, I guess.
Okay. Thank you very much, Marcus.
Yes, please.
Excuse me, thank you very much for the lecture. I don't know how can estimate the mixing ratio after burning or before burning.
With Raman, I mean, it's very simple. If I would say that if Raman can be used, Raman should always be used.
Burning,
After burning, after.
Oxygen and
Yeah. I mean, in the afterburning, and if you have optical excess, and if you don't need 2D images, Raman for point-wise measurements is unbeatable because you can directly.
because oxygen and fuel is consumed.
Yeah, but I mean.
It's a chamber. Oxygen and.
Yeah, but you measure. I mean, in the measuring point, you measure how much oxygen you have. And you can measure time, as I showed, time in time sequences. So you can see when and how it is consumed. And you can convert this to absolute air-fuel ratio. As I showed in the engine, I mean, we measure the oxygen peak, you measure the fuel peak, and then you just take the ratio directly, you get the air-fuel ratio. You don't have the problem as we had in the laser-induced fluorescence with all this quenching and all of this. Okay.
Next workshop will be held after lunch. We can do some discussion after the end of the decision. Thank you very much.
Thank you.
Yes, sir, I am.
Pardon me. We should move very soon to Amazon lunch.
I thought we had to 12, right?
Yeah, but we have to wait. And also.
Okay.
I am associate professor of university. How can I go to your lab for research?